to talk about the somewhat controversial topic of implicit regularization. So, so take it away. Thanks. Thank you.
Okay, I didn't know implicit regularization was controversial, so please don't eat me alive. Yes, thank you, Adam, and thank you all for coming for the last talk. It's great to be here, especially since it's also like the first time I'm outside of my hometown in pandemic. So today the core focus of my talk would be function space view of norm minimization. And for the main results I'll be talking about will be in the special case of linear coordinates, where we can we'll define the problem and see some interesting results. Much of the results I'll be talking about, especially in the second half, is based on a paper which is joint work with Meena Jagdishan, who's a student here, and probably she's not here, but she's a student in Berkeley, who's also a primary driver of this project, and Ilya Razerstein, who was a colleague of mine in MSR before he's started a startup on his own. But before we dive down into this very specific and narrow topic, I wanted to give a broader overview of some of the motivation and thought process and results in learning over parameterized models. And specifically here, want to focus on how the inductive bias from algorithms, architectures, and data differ from how we thought about these choices in traditional machine learning, where we didn't have over parameterization and the models were much more well specified. And although it's a little early, I wanted to introduce the notation for the talk so that we can keep it consistent throughout the talk. So, and that's also a good way to introduce the three components I talked about. So we'll denote data sets throughout as D, and I mean, the goal we'll be focusing on is like learning tasks, where we collect an observation of typical samples X, Y. I'm writing much of the problems in the notation of supervised learning, but it also extends to unsupervised learning and self-supervised learning. So Y is really matters only for the loss, but X is the main component we care about, which is the input data. And the second thing we pick is like a model class or architecture. So this is the family of candidate functions we want to consider for this task. And specifically, we'll be looking at parametric family of functions, where the function class is denoted by parameters I will throughout the talk denote as theta. Here, I want to introduce two notation. One is that of phi. Phi essentially represents the class of functions I care about. So it's a mapping from the parameters to the set of functions. So it takes in a parameter and gives out an output, which is the output is essentially a function over the inputs. And then the second notation I talk about is like f phi, which is essentially a mapping you can think of as a mapping between the parameters and the input. So this is the one which gives you the actual output. So if you want to keep neural networks in mind, theta represents the weights of the neural network. Phi is kind of like the architecture. It's a architecture of the neural network, which specifies how given theta you construct the function. And f theta of x is essentially like the function computed on with parameters theta and input x. And finally, like the most important component of many learning problems is some sort of loss minimization using various algorithms, training techniques, and heuristics, and so on, where you have some predefined loss over the outputs of your function and your labels or whatever you expect as an output. And you want to minimize this loss over the observed data set we collected in the beginning for this task. And this in some sense are like very core components of learning. And what makes a problem over parameterized is there are various definitions. You can start from number of parameters, but a functional definition we'll be working with today is these are problems where the loss functions we wrote, which is like just training loss over observed data set, has many solutions which perfectly fit the data. So these are like fundamentally ill-posed optimization problems by itself, where the loss has many solutions which perfectly fit the data. On the other hand, if you give me just any argument, it's not likely that it will do well on my task. So the other aspect of overparameterization, most minimizers of the training loss are going to be poor performers for the task we care about. So this will kind of keep as a functional definition of overparameterization. And the super toy example is like, we probably have seen it like in introductory machine learning class. If you have like a linear regression problem in one dimension, and you have some data points which we want to fit with not linear regression, we want to fit the data points with a function. If you don't constrain the class of functions, there are many ways to fit it. I can fit with a bizarre looking function like this, or I can also fit with like nice functions like some linear interpolation or smooth interpolation and so on. And if you just think about like laws in terms of the observed examples, like all of these, and we don't constrain the function class, all of these are valid minimizers of the laws. So the laws by itself does not distinguish between any of the minimizers. So when we are working with losses, training losses which are of this form, then every choice we make along the way to pick a specific model becomes important for defining the inductive bias of the learning process. For example, every algorithmic choice we make, every algorithmic choice we make, hyperparameter choice we make will change what specific solution we pick from this large class of functions. So the TLDR is that optimization objective itself in overparameterized models, like optimization objective itself is insufficient to specify the real inductive bias. Rather, the models learned crucially depend on the training algorithms, which has been a focus on a lot of the study recently, where training algorithms here include all the hyperparameters, where you can think of the loss landscape as having many minimizers, and different algorithms essentially choose to take a different trajectory through which to reach a minimizer. And so, and this is also affected by the initialization, step size, and a lot of other hyperparameter choices. And the specific inductive biases you get from training algorithms, we've been referring to as implicit bias, implicit regularization, or implicit inductive bias from algorithm. So another thing which kind of relates to training algorithm, but which has a kind of complementary influence is the architecture or parameterization. So even if you take if you fix this training algorithm you care about as SGD, by changing the parameterization, you are changing the loss landscape and hence the geometry in which you look. So if you, for example, if you think about SGD, it is an iterative procedure where at each point it looks for the steepest descent direction in the parameter space. So now if you change the parameterization of a function, it changes what the steepest direction looks like. So it changes the trajectory. Yeah, so architecture again plays an important role in defining the implicit bias from training algorithms. And one of the things we don't talk about when many of the works talking about implicit regularization is like the role of data and data augmentation. And this is something I won't touch upon either, but I think it plays an important role in overparameterized learning too, and having some kind of an understanding in this space would also be very useful. So this is more of like something I would like to see more of and personally like to work on more of kind of a thing. But I'll mostly give an overview of the what we know about how training algorithms influence the inductive bias, and mainly focus on the second bullet point, which is how a specific parameterization or architecture can influence the inductive bias. So here I want to emphasize, yeah.
I mean, when you say optimization of if I include a regularizer in my optimization objective, then regardless of what algorithm I use to minimize it, it will generalize.
If you can guarantee that you will minimize the regularized objective to global minimizer. Yes, in convex problems, if you include a regularizer, then yeah, this is not no longer an overparameterized.
Assuming you can do VRM and you can include that in your optimization.
Yes, if you can for convex problems, you can always include it.
Just assuming I can do VRM.
So you can guarantee that you can minimize a regularized objective, then yeah, then the objective you are minimizing over is no longer overparameterized. So yeah, so that's why I wrote the definition to be in this form, where like I only care about these topics when I can reach multiple solutions which depend upon the algorithms. Yeah, and like defining putting. Yeah. Is that okay? So here I want to specifically highlight that it's not like training algorithms and architectures don't matter in like non-overparameterized regime. But what I want to emphasize is like they play a role beyond what they were originally intended for. Training algorithms, of course, are important to see how fast we converge, and like even if you have a well-posed problem, they are important for various learning setting. But here I'm saying that beyond just optimizing the objective, they have a new role which they play where they drive the implicit inductive bias. And similarly with architecture and parameterization, once you define an architecture, it has a natural capacity control. So we define architecture so that you only look at functions which are realizable by that architecture. But here I'm saying, here I want to emphasize that the role of architecture extends beyond that explicit characterization, and it also influences the implicit bias from optimization by changing the trajectory. So in some sense, like all of these always had a role in learning. Here they wear a slightly different hat, which we want to understand better. Okay, so in terms of overview, I wanted to first just take 5 more minutes to talk about training algorithms, like what we kind of understand about training algorithms, and also mainly to give some specific examples to clarify this. And I apologize for any of you who have heard me talk about implicit bias multiple times, so sorry for the repetition, but I think I'll not spend too much time on this topic. So just to give you a preview of the many results we know on implicit inductive bias from optimization algorithm. So here, the style of results we care about are like we define a loss function which is over parameterized by the definition I gave earlier, and we try to understand how different algorithms and hyperparameter choices lead to what kind of solutions are obtained by different algorithms. And this is a very, very active area of research. Many results are recent, but it's also it's not something very new to neural networks. There have been results about how optimization can drive special inductive biases in boosting literature and perceptrons, like some of the oldest algorithms we know in ML2. This is a very, very selected subset of reference list, and I can give an entire tutorial on these topics for multiple hours. So, but broadly, I've been there have been a lot of, I've categorized as some broad themes. There have been a lot of work before we started looking at it in the context of deep learning, as I said, in boosting algorithms and perceptrons and so on. And then we also had a sequence of work which empirically demonstrated that, even for the same objective, different optimization algorithms can get you to different solution, which will have different generalization performance. So here it's a style of problems where you have a fixed network, fixed data set, so fixed loss, and then different algorithms lead you to different solutions. And then we had a sequence of work on analyzing the nature of this implicit bias in a very explicit form, characterizing it in a very concrete and quantitative form in many linear models, because these analyses are already hard for linear models. It's usually very hard to do it in this level of generality in non-linear models. And there's also so we had a bunch of results in linear models, and also asymptotic results when you have logistic loss. I'll talk a little bit more about it in a minute, so I'm going to skip that bullet point. And finally, there are also a lot of work which try to analyze gradient descent in large width neural networks in this so-called NTK or neural tangent kernel regime, where you can show that if you're really, really over parameterized compared to the size of the initialization or the size of the output, then you essentially work like kernel functions, and you can explicitly characterize what the gradient descent trajectory will look like. And finally, there are also while many of these kind of try to say that gradient descent gives you some kind of an implicit regularization of some function. So it's kind of the style of results are gradient descent converges to a solution which minimizes some other regularization, but it does it implicitly. There are also results showing that it can have a generalization performance without minimizing any kind of explicit regularizer. So, and there are many work on this topic too recently. Okay, so I want to just give one set of results in detail, just to highlight the differences I was talking about earlier in terms of architecture choice and algorithm choice. So this would be a very simple problem of separable linear classification. So you have a classification problem, but it's a linear classification problem where you have +1s and -1 data points, but it is linearly separable. So you can fit a line which gives a perfect classification accuracy. And then we'll be looking at loss minimization with so-called exponential tail loss, and the most common case is logistic loss. You can also think of exponential loss if you haven't seen logistic loss before. But the property we care about is that it's a function of just the inner product of the linear predictor and input, and it never reaches 0. So it's always decaying. So like with logistic loss, you never reach the minimum of this logistic loss with any finite value of W. So W are the parameters of your linear model, and you never reach 0 with any finite value. So in some sense, this is, although it's a convex problem, if the data is linearly separable, this doesn't have any finite minimizer. So it asymptotes towards 0 loss as the norm of W goes to infinity. So because this is a convex problem, if I take small enough step size and run gradient descent, your norms will diverge. You're not going to converge to anything. But for classification problems, at least if we don't care about calibration, we don't care about like the prediction. We don't care about the norm of W. We only care about what the direction of W is, because that defines the classification decision boundary, right? And now we can talk about, like, if the data set is separable, clearly, like, you can come up with different separating hyperplanes, and each of them is a valid classifier. So now if I take any of these hyperplanes and take the norm to infinity, like, that will minimize the loss. So it's ill-posed in two ways, that there is no finite minimizers, and also if among all the solutions which can go to, among all the directions in which it can diverge, and there are many directions which will minimize the loss. So the question we can ask is, like, in this problem, like, if I run some out of the box algorithm, what classifier do we converge to, right? And some theorems I haven't given reference, but here, but like, it's in a bunch of papers. It has been invented and reinvented many times. So my claim is that if you run just gradient descent or stochastic gradient descent, which is mini-batch stochastic gradient descent here specifically, if you run gradient descent on this problem and then just like look at what the asymptotic result is, which is like let the norms diverge and then look at what the classifier you're getting, you can show that this classifier you get is like the minimum, the max margin solution, which essentially minimizes L2 norm of the parameters subject to fitting the data with a positive margin. So this is what I mean by the implicit bias here, because here you get this L2 norm implicitly from running gradient descent. We didn't have an L2 norm regularizer explicitly in the objective. And to see the contrast, if instead of running gradient descent, if I take the same objective and the same parameterization and instead run gradient descent or boosting with like appropriately chosen step sizes, you can show that it converges into a very different solution, which is like the maximum L1 norms, L1 margin solution. So you can, even in this simplest linear model case, you can see that you get very different solution depending upon the problem, depending upon the algorithms you choose. And here we are still sticking with simple local search algorithms. We have just changed the geometry from gradient descent to coordinate descent in the parameter space. And if I can do something even more crazier, where instead of doing gradient descent on the subjective as is, I'm going to write a different equivalent parameterization of linear models, where I'm going to write W as U square minus V square, where U and V are d-dimensional vectors, and like the squares are element Y square. So it's essentially writing each coordinate as U square minus V square. And then now I can run gradient descent on U and V. So this is a non-convex problem. It doesn't converge always, but we can characterize when it will converge. If you believe that it will converge, it does converge to a global minimizer, then we can explicitly characterize that the specific solution I converge to is again an L1 margin solution. So here you have like is a contrast where this difference between L2 and L1 arises because I changed the algorithm, whereas this difference between L2 and L1 arises because I changed the parameterization. I've kept the algorithm the same. So in some sense, you cannot separate the algorithm from the parameterization because they together define what happens in the function space. Does this example make sense, kind of? Okay, yeah. Okay, so I just wanted to give this example to clarify how these things interact and the fact that each of them influences the other. In fact, I didn't want to overload it, but one other block we can add here is like, for this problem, if you do early stopping or take initialization to be very large, you can also show that it goes very close to the L2 norm solution, L2 max margin solution. So you can track the entire trajectory, and you can show that because these are asymptotic results, if I don't do asymptotic result, it kind of like, you can approximate it with an interpolation between max L1 norm solution and max L2 margin solution once in some regime. But okay, so So that was an overview of the thing. So now I just wanted to state one more theorem, which is important for why we care about the function space view of norm minimization. So there has been, like I said, there has been a lot of work in trying to understand this problem, specifically for gradient descent. And one most general result, which is of interest, is that for homogeneous models. So recall that we specified this notation phi, which essentially is a mapping from parameters to function space. We say this architecture is homogeneous if every time I scale a parameter by a scalar alpha, like the output, positive scalar alpha, the output only scales by an alpha. So the direction of the output remains the same, but it only scales by alpha, right? So,
Exactly alpha.
oh, sorry, it's some scalar function of alpha. Yeah, sorry. It's a scalar function of alpha, it's fine. So in some sense, if you're thinking classification decision boundaries, it only increases the norm, but like doesn't change the signs or any of the things. So in particular, all linear networks and ReLU networks without residual connections satisfy it. It's not all the networks we use in practice. In fact, most networks we use in practice have residual connections or bias terms, but this covers a significantly large fraction of networks of interest. And here we can state this theorem where we can say that for positive homogeneous models, if you are minimizing logistic loss over this or cross entropy loss for that matter, so the assumption is like the gradient descent trajectory at some point classifies the data correctly. So at some point your training error becomes small, becomes low. So it perfectly interpolates the data. And in that regime, if you keep training the algorithm for longer and longer, it will asymptotically converge towards stationary points of this optimization problem I wrote here, which essentially minimizes L2 norm of the parameters subject to fitting the data. So here, specifically, this theta here is like the parameters, not the function space L2 norm. In the previous slide, when I was talking about linear models, the W was representing the function, like rather than the parameters. I mean, for pure linear models, it's exactly like the same thing. But here, I'm specifically talking about L2 norm in the parameter space. So there is a caveat here that we can only show that it converges to the direction of limit points converges to stationary points of the subjective, but for example, it does not mean that it will converge to stationary points, any interesting points in the function space. But this is a pretty substantial result of interest, and that motivates us to actually study what does this even mean? What does this bias even mean in the function space? So if I'm minimizing L2 norm of the parameters, what does it mean in the function space? What am I doing in the function space?
You're saying it won't necessarily find its solution per se.
Yeah. It won't necessarily find a solution, but this is like the state of theory. There is enough connections, and so this motivates what happens in the function space, and also like that also motivates, if we can say something in the function space, we can also test it on networks of interest. Okay. Yeah.
If the trajectory separates the data.
Sorry for the terminology. It essentially means that at some point you have a perfect classification.
Okay, so
And then, but you still,
once on your data.
and then you continue training with,
Sorry, maybe what does it mean for the stationary point basically being a particle plane?
okay. So stationary point, the stationary points are limit points. The stationary points is like the first order KKT conditions of the subjective.
So if you move it,
Yeah, it moves to it satisfies. So you run gradient descent on the subjective, you look at the direction classification boundary, and in the parameter space, it satisfies the first order stationary KKT conditions of this problem. Okay, so this motivates us to separate out the role of architecture slightly. So let's say this is not a complete theorem. This doesn't hold for many loss functions, and it's also asymptotic result. Plus, we have the caveat of stationary points. But if you think that this is an interesting inductive bias of interest where we are minimizing L2 norm of parameters, then you have an interesting class of problems where we separate like all this gradient descent and algorithmic implicit regularization, and just study what does minimizing L2 norm in the parameter space even mean in terms of inductive bias. So that's a focus of like this. How much time do I have? Okay, sounds good. Good. So that will be the focus of this part of my talk. So you had a question, Adil? Yeah. Okay. Part of the talk. So although I motivated it from an implicit regularization perspective, where we showed some connections to L2 norm minimization, in general, weight norm based capacity control is pretty ubiquitous in neural network. You also have like explicit regularization, although here again, we cannot guarantee that you will converge to a minimum L2 norm solution. But we also have connections to implicit regularization in various settings I described above, where the idea is like the L2 norm of parameters comes up as like minimizing the L2 norm of parameters comes up as an interesting inductive bias, right? Just to clarify, this is not the only interesting inductive bias. In fact, many other forms of capacity control are also proposed, have also been shown to be shown to hold in the case of gradient descent in over parameterized models, but we'll think about this as it is one of the important inductive biases, right? So then we can ask, what is the function space view of controlling it? So this is a cartoon picture you can keep in mind. You have a parameter space W, and then you constrain the parameter space to be in a small norm ball, let's say. And then we are trying to answer what does, and then there is a mapping which takes a parameter to functions. And we are trying to answer what does this ball look like in the function space. And this can be very different for different parameterization speed. And we can capture exactly this phenomenon by this induced regularizer, which we can think of as like representation cost of realizing a function in terms of the norm of the parameters. So, so I define this capacity over the function space, which is the infimum of all the parameters, which can realize the function exactly on all the data of interest. Here I've just written it as input space, but you can also, and I will mostly be working with unconstrained input space. But this is the definition of the induced regularizer. So you can say that this regularizer is defined for any function because I have written inf. So if a function is not realizable by the architecture, this will be infinity. On the other hand, if any function is realizable by the architecture, and if it is realizable by multiple parameterization, you pick what is the minimum cost I need to pay in terms of L2 norm of the parameters in order to realize this function. And you can also check that this is of interest, because if we were able to actually minimize L2 norm of parameter L2 regularized objective, that is exactly equivalent to minimizing this induced regularizer subject to fitting the data. Although this equivalence holds only for global minimizers and not for stationary points, but like this already shows that there is this regularizer is of interest if we care about L2 norm of parameters as an important inductive bias. And so now we can ask for different architectures, what does this function look like? And many cases we can, although I've written it in terms of infimum norm, in many cases it's not even a norm, and it's of interest how different architectures influence this function. Some simple cases where we can quantify it is like if you had a fully connected linear network. So it's just a linear model which it's take a fully connected network and remove all non-linearities. And then you can show that the induced regularizer over the linear models is just the L2 norm of the linear models. On the other hand, this is something we'll revisit in a minute. If you have like a convolutional network where each intermediate layer is a full dimensional convolution, you can show that, and you have like L layers, you can show that the induced regularizer is a 2 by L quasi norm in the Fourier space. DFT is like this discrete Fourier space. And we'll revisit this in a minute, so I'm not going to go into the detail. There are a few other places where we kind of explicitly know this answer. For matrix factorization, you can show it to be the nuclear norm of the matrix. And somewhat more interestingly, if you take infinite width networks with ReLU activation and try to ask what is the minimum cost like required to realize a function. For scalar function, you can relate the induced regularizer to some form of correction on the smoothing, total variation norm on second derivative with some corrections. The star here denotes some correction terms I didn't want to go into because it will take a while to explain that. And there is also generalizations of this for large width but not infinite width and non-scalar functions and so on. So next 10 minutes I'll focus on like studying this problem specifically for linear convolutional networks, and we'll focus on how different channels and kernel sizes could influence the inductive bias. So let's define a 2-layer linear convolution network. So you have the inputs, your first layer is obtained by just a convolution with set of weights, set of first layer weights, and let's say the kernel size we look is k. And then the second layer is just a linear combination of the first layer weights. So in this case, you can write the end-to-end linear predictor as u convolved with v. The down arrow essentially is a permutation of the coordinates. So for the purpose of this talk, like you can ignore the down arrows. You can say that the linear function, because you can just might as well define v down arrow as like your parameter. Purpose of this talk, like the end-to-end linear function realized by this tiny network is essentially just u convolved with v, where u are the weights of the first layer and v are the weights of the second layer. And the induced bias in turn is like what is the minimum L2 norm of u and v such that you realize a linear function. So one other thing is like I'm talking about full circular convolution here, but you can simulate zero padded convolution with circular convolution in a higher dimensional space. So I'm not going to go into the details of the differences. Okay. So okay, what is the trick here? So take a special case when k equal to d. So it is a case of when k is full dimensional kernel. In that case, we can do a Fourier trick where we can look at the entire operation in the Fourier domain. And it becomes a much simpler model to analyze, where it looks like your W hat, which is the Fourier discrete Fourier transform of the end-to-end linear predictor, is just element-wise product of discrete Fourier transform of u and v. And now you can clearly see why you will get minimum L1 norm, because so you can write the induced regularizer as in the Fourier space as, because the Fourier transformation is norm preserving, you can write it as the minimum norm required to realize a particular Fourier matrix, a particular Fourier transform of the linear predictor as a product of u and v. And here you can, if there is no constraint on what u can be, if there is u is full dimensional, then you can just use simple am greater than gm inequalities to show that this has to be L1 norm in the Fourier space. But when you have like, when you use a smaller dimensional kernels, which is what used in most times in practice, you have a constraint on u. So for example, if in the other extreme case of k equal to 1, where you're just doing a one convolution, which is also an extreme case, your u hat is restricted to be in a certain lower dimensional space. It cannot take any values. And so I cannot pick u hat to satisfy this property. And as a consequence, you can actually show that in this case, when k equal to 1, the induced regularizer is actually like the L2 norm, or is a scaling of the L2 norm. So in other words, you have these two extremes as a function of k equal to 1 and k equal to d. And although, like I said, I computed this without thinking about gradient descent, you can take some simple MNIST binary classification problems and try to see what happens if I run gradient descent with k equal to 1 and k equal to d. So this is a binary MNIST classification between 1 and 0. And then the top left is the signals. And I look at the final linear predictor obtained by gradient descent. So the left column is like the signal space representation, which is just W as represented. And the right space is the Fourier domain representation. So for k equal to 1, you have like a concentration. It's almost like a minimum L2 norm solution. So you have a concentration in the center where you see most of the data points, and then there is zeros everywhere. And there is no structure in the Fourier space. On the other hand, when you have like k equal to d, you have this repeated patterns of observing 1 in multiple locations. So it's some sense it's like trying to minimize the frequency, trying to introduce sparsity in the frequency domain by repeating the signals in multiple locations. You can see like how this might somewhat contribute to notions of translation invariance and so on more than the first one. And but unfortunately, for intermediate case, in general, it is very hard to get a closed form solution. In fact, the algebra gets very complicated even for k equal to 2. But nevertheless, if you look at what gradient descent returns, you can see that this is for k equal to 1, 5, 16, and 28. It slowly builds up it's almost like an interpolation. I cannot say it with guarantee as yet, but it's almost like an interpolation between these two extremes in the Fourier space. And so the question we can ask is, like, can we actually quantify this as an interpolation, or can we say something more even if we cannot give a closed form solution? And the answer is yes, which also led to a more interesting discovery. So the key technique we can use is like an SDP relaxation. So if for two-layer networks, all these, if you work hard enough, like you can write most of the objectives and the constraints as some form of as an SDP with additional constraints. So in particular, for this case, you can write the objective as a linear function of some lifted matrix. And same with the constraints, we can write the constraints as a linear function of some lifted matrix, which where I'm essentially stacking U and V into a tall column and then taking UV transpose to get this kind of a lifted matrix, right? And so like for this problem, I can define Rk of W exactly as this SDP with a rank constraint. Right? Because I need the rank constraint because I have constructed this by looking at Ws which are rank 1. Okay? And this naturally gives you an SDP relaxation like every time where you can just drop the rank constraint. Right? So so I've taken like the two-layer network and like shown that like the objective and the computation of this induced regularizer can be written as an SDP with some rank constraint, and I can drop the rank constraint. And the interesting thing about this this SDP is that if you have multiple channels, which is very common, this SDP kind of generalizes. So the math is like, you can check the math later, but it's essentially like the same convolutions, but instead of having one filter, we have multiple filters. Okay? So if you have multiple filters, you still learn a linear function. And but in this case, the exact characterization becomes an SDP with a rank constraint where rank is less than the number of output channels. C out is the number of output channels. So again, we can drop the rank constraint to get an SDP relaxation. And a key theorem we prove is, a key and surprising theorem we prove is that for two-layer convolution networks, this SDP is tight for all values of the channels, which essentially says that it doesn't matter what the number of output channels are, the representation cost is going to be the same. So in some sense, you're going to have invariance to the number of output channels when you have two-layer linear networks. And yeah, so so that's a key. And then the main takeaway is that the induced regularizer is indeed independent of the number of output channels. And the other information we get is like, because SDP is a convex problem, the induced regularizer is also a norm. At least for two-layer networks, we know that we now know that it's a norm. And we know the extremes of the two norms, and we can show that it interpolate. Now we can quantitatively show that the solution we get will be an interpolation between L2 norm and the L1 norm in the Fourier space. And in particular, we can also get like bounds on when it will be closer to L2 norm and when it will be closer to L1 norm. So I had like I don't have time to go into it, but I really like the proof technique we used here. So I wanted to give some high-level comments on it. So one is like, if we just look at this SDP, we know that even just looking at the SDP, we know that once C out is larger than the size of W, it stops mattering, right? So that's an obvious fact because the rank of W is like at most going to be, it's a square matrix. So once it's larger than the dimension of W, it stops mattering. So it's with a little bit of extra work, we can show that every KKT solution of this problem of this SDP will also have rank at most k, where k is the number of channels. Sorry, k is the kernel size. So that's also not hard to say. You can just look at the KKT matrices and then you can get it very easily. But the tricky part is to showing the gap between when the rank is less than k versus any rank constraint. So essentially showing that between the number of output channels being less than k versus the regularizer being independent of all of C out completely is the main tricky part of the proof. And in fact, like we can construct solutions of this SDP which are not rank 1, but the way we prove this is like for every such solution, we can implicitly show that there exists a rank 1 solution with the same objective. So if you give me a solution of this SDP which is not rank 1, I can show that there exists some other solution of this SDP with the same objective and satisfying the constraints, and it's rank 1, and hence shows the tiredness. And the key lemma we use here is like, if you think of convolutions in D dimension, where D is greater than K, And the key lemma we use is like if you take any two vectors A and B which are on k dimensional and pad it with zeros so that you make it d-dimensional and do convolutions on those vectors, then you can say that you can add any such number of vectors, A convolution A, B convolution B, and there exists a single C such that C convolution C matches this left-hand side. And so matches this left-hand side, and also C is of like k sparse. So it has only k coordinate, top k coordinates which are non-zero. So this is a tricky part, and the proof idea itself is very cute, which Meena came up with, which is to look at all these operations in the polynomial space. So think of every vector as a polynomial, is a degree k polynomials, and look at all the vectors in so all these operations as a polynomial operations. And then you can argue about the roots of the polynomials to show that there should exist such a C which will satisfy the constraint. And I think the proof technique itself is like very novel, and like it's very interesting to look at. Anyway, but since I'm out of time, I'm gonna like end close to with some more empirical examples. So here we previously saw like MNIST classification problems, and where we saw what happens for different values of k. Now we look at the same problem for different values of C, and we see that again, like even though we didn't explicitly analyze gradient descent, the conclusions from our theory on representation cost kind of extend. So for k equal to 1 to for C is like number of output channels 1 to 4, both in the signal space and the Fourier space, you have equivalent relationships. Visually, you can also quantify this. Okay, I don't have the quantifications for linear models. You can also quantify it by measuring the R of beta values, because it's we know that it's a convex problem, so we can explicitly measure it. So the more interesting thing which came out of our empirical study is like we had a theory only for this linear models. Then we can ask the question of, does it also extend to nonlinear models? Can we also say something about nonlinear models? And at least in our preliminary experiments, it looks like the invariance to number of channels also holds when you have like nonlinear ReLU activations. And so here on the top, so on the top row we have various kernel sizes. On the columns we have various kernel sizes, and on the rows you have various channel sizes. And you see that like the variation within channels is much smaller than variation across kernel sizes. There is still some variation within each channels, but in the paper we also have standard deviations which show that it's within the. So you can run this multiple times, and you can show that these values are within the standard deviations. The error bars overlap across these values. So this is interesting instance where we had a theory for purely linear models, but then it gave a concrete testable hypothesis, which is like what is the role of number of output channels in 2-layer networks, which we can actually test on nonlinear networks and derive some conclusions about it. Sorry. So finally, sorry for going over time. I just wanted to give concluding. So I also wanted to state that although I talked mainly about single input channel networks, we also have results for multiple input channel networks, which is also more common in the paper, and both experimental and theoretical results. But I won't get to go into it today. Just leave you with some concluding remarks. Like I said, I wanted to reiterate that in learning over parameterized models, every single choice you make kind of contributes to the inductive bias. And previously, we have had a lot of work on understanding the inductive bias from an algorithm's perspective. And this is a pivot to try to understand it from the parameterization or architecture perspective. And I specifically, like the main results I showed are in the case of like linear convolutional networks, where we could derive some interesting conclusions about the role of in channel size for single channel inputs by looking at the representation cost. And so I will stop here. I wanted to give you a preview of like there is another aspect which I didn't talk about, which is the role of data augmentation. Just wanted to leave this slide here, where you can see that we can talk all about different architectures, but once you have enough data augmentation, the performance of different architectures kind of closes. So in some sense, this is also showing that the data augmentation plays an important role, and I wanted to just pitch it as a research problem to pursue theoretically. So thank you for your time.
Okay, since we're so over time, let's just take questions just right afterwards. And thanks for coming to the workshop. Thanks.